Are we live?
Yes.
Amazing. Hello and welcome, everyone. Welcome to the Audio Programmer Virtual Meetup. This is, if I count correctly, the 9th time we're doing this. We started this in March. So we are still going. And thank you so much for tuning in again for those of you who have watched the previous episodes and being part of this. I'm really, really excited to be here. My name is Timur Dumle. You might also know me as Timur_audio from Twitter. And I'll be your host tonight together with Josh Hodge. Hello, Josh. How are you doing?
I'm great. And it's really an honor to have all of you here with us today, both people that are watching and also people that are joining us today. Some really amazing people here on the call today, and we hope that we have a fantastic meetup. So a couple quick announcements. First announcement is, once again, we're always looking for other people to speak at the meetup, and you don't have to be a legend like all of these people here on the call to actually present. And you can actually submit a proposal via the Audio Programmer website at theaudioprogrammer.com/submit. Also, we have our Audio Programmer community where developers help each other solve audio programming problems and help counsel each other on their audio programming woes. And we have developers of all levels, and you can come join us on theaudioprogrammer.com/community. So that's our Discord group where we have over 4,000 people that are from worldwide helping each other out. Final thing about the Audio Programmer is that we've actually started some new pages, and I'm going to put my screen up here right now. The speakers can't see it, but essentially we've, some people may know that we've been working as a development agency, recruitment agency for some time, and that, sorry, my dog, she always makes herself known. And what we've done is we've actually set up two new pages on theaudioprogrammer.com. We have one that is for roles. So we have companies that come to us sometimes looking for us to help them fill a role if they're looking for an audio programmer. And we also have another one for candidates. So for experienced candidates that are actually looking for new opportunities as well. So if you're a company, you're looking for a DSP specialist or a game audio engineer, we actually have some candidates that are actually becoming available now, and you can find those all on theaudioprogrammer.com. And so last thing is that we have ADC coming in a week, and Timur is going to speak a little bit more about that. So take it away, Timur.
Yes, so ADC is coming up next week, and we actually, as it looks like now, the program is coming together really nicely. So I'm happy to announce actually the 2 keynotes that we're going to have. So we're going to have an opening keynote by Anna Przeworowska from Ableton, and she's going to talk to us about entry points to innovation. And then the closing keynote is going to be Kelly Snook talking to us about investigative music, building musical instruments to understand realities. And Kelly Snook is working on the Kepler Concordia project. So if you want to know what that's going to be about, join ADC. You can still register by going to audio.dev and clicking on tickets. And yeah, I'm really excited to see you all there.
Yeah, and I have one more thing. We don't want to forget our sponsors that have helped to make this possible. So of course, Juice, who have also helped to make ADC happen. So Juice are sponsoring the Audio Programmer Meetup, and we appreciate their support, along with Focusrite and the good people at Sonux. So thank you to our sponsors for their support.
Thank you, Josh. And with that, we come to the meat of this session, which is our wonderful guests. So we have 3 guests tonight for you. Matthew Fetcher, Kennard Garrett, and Fabian Renn-Giles. Do you want to just briefly say hello? How are you doing, guys?
Yeah, good. It's cold here in Berlin, but it's good.
Yeah, great.
Yeah, it's warm here in Atlanta, and we're so honored to be on this meetup.
Yeah, same here. I'm calling in from Atlanta. It's a dreary day, but it's nice and warm. And once again, it is an honor to be on this meetup.
Well, it is really exciting to have you here. So we are going to do a Q&A with you, Matthew, and Kennard later. But before we come to that, we have Fabian Renn-Giles, who is going to talk to us about the Linux audio API. And so Fabian and I have met, I think, was it 5.5 years ago now, when you both joined Rolly about the same time, and we're working on the Juice team together. So that was a pretty good time. And now, Fabian, I think you're going to be telling us yourself what you're up to these days. I'm really curious to find out, and I'm going to give the stage to you. Welcome to Fabian.
Okay, thank you so much, Timur. And it's such an honor to be on this meetup, sharing the stage with some of these great people and some of the previous guests. And I'm so happy to see the audio meetup is in such good hands. So let me get my screen started. I should have said these words while this slideshow loads, because it takes an a long time to load on my machine. So I wish I could do some theme music now, but I can't. So we'll just have to wait until the spinner spins. Anyway, almost there. There we go. Okay, so as Tim already mentioned, this is about the Linux Audio API, a different way to do audio. I'm Fabian Renn-Giles. I am a contractor, freelancer, and worked with all of these great companies you see here, or doing projects with them. And the meat of this talk is the work that I did with Sing here in the middle. So I'm giving them an extra sparkle. So I've been working with Sing now for 2.5 years, I think. And yeah, most of the insights in this talk came with working with them. So just a quick overview of this talk. There'll be an introduction. Then we're going to talk about sort of the key stages when dealing with an audio device API, which is sort of, the main I/O loop, opening an audio device, configuring an audio device. And then there's going to be a section of what we actually mean when we say buffer size. And then there's this last section where we talk about timing. So as always, if you've been to one of my talks before, I have talk disclaimers at the beginning of all my talks. And the big disclaimer here is that this talk is about the concepts and the ideas behind the ALSA API. So I'm not talking about, the ALSA code as such, but just about the ideas behind the API. And I really want to stress that some of these API calls, they're not even implemented, right? So I really just want to say, like, the person who came up with the idea for this API, and talk about the key concepts here. But if you want to use this API, this is the wrong talk, right? Because some of the APIs I mentioned, they're actually not even implemented on Linux. So this talk is not how to use ALSA in practice. And you will definitely not learn how to use ALSA in this talk. Disclaimer number 2 is all the code shown here is pseudocode. Normally the function calls will be the correct ones, but the number of parameters, I may have omitted a few, or these are all C APIs, so I sometimes have multiple return values, which C API normally don't have. I will mostly only discuss the playback case, but the capture case is usually just as equivalent. And I often compare the code to core audio, but really core audio is just a stand-in for like traditional audio APIs. For example, Juice or Port Audio all use sort of the same style of audio API. So when I say core audio, you can also replace that with Juice or Port Audio or any other audio API. Also, just to stress, and I know this is going to be maybe disappointing for some, really this talk is for people who have done some low-level audio development before. So this is an expert talk, right? So it's probably more for people who maybe want to design their own audio API, so library developers or anybody looking to do embedded software or hardware development, or maybe if you just want to understand how audio hardware works. So maybe if you're not, even though you might not be a super proficient low-level audio developer, maybe just seeing some of the concepts in this talk helps you to understand how audio hardware actually works. So let's get to the meat of it. What is ALSA? Well, it stands for Advanced Linux Sound Architecture, and as the name says, it's a Linux API. And it's the lowest level API that you can have on Linux, right? When you write an audio app. So this compares with Core Audio on macOS or Wasapi on Windows. And just to be very, very clear, of course, there are many other audio APIs, for example, Juice, but any other API on Mac, Windows, or Linux will at some point call into these low-level APIs, because that's the only way at the end of the day how you can get audio out of the system, right? So there might be really, really nice audio wrappers on Linux, like Juice, for example, but this is not what I'm talking about. I'm talking about this lowest level of audio. And when I compare it to other operating systems, I'm always comparing this low-level API. Sort of from a bird, now ALSA running on Linux has a really, really large market and target audience. And this makes it very, very challenging to develop a good API. You know, you have embedded devices running Linux, low memory footprint, low CPU, you have mobile phones, you have low power, you have, you know, desktop consumer audio, you know, constantly switching audio jacks, headphones, video cameras, etc. Then you have sort of more on Linux these days, you can do Pro Audio. Probably wouldn't recommend it, but you can. And then, you know, some of these really high-end professional broadcasting boxes you would find in the BBC, these rack-mounted units, they often run a Linux operating system. So we have this huge range of devices that ALSA needs to cater for. And that makes it very, very challenging to write a good API. And this is now the sort of the bird's eye view of ALSA. You have your audio app that will talk to a library, a user space library, the ALSA library, which then talks to sort of the kernel API, which then somehow, you know, talks to the ALSA kernel driver, your audio card driver, which then speaks to the actual hardware. And this is not unusual. This is how it works on Mac with Core Audio. This is how it works on Windows with Wasapi. This is not unusual at all. Maybe a bit interesting is because ALSA is so low level and has so many use cases, the ALSA library provides different levels of API. So they don't have a single API entry point. They have a sort of an easy entry point and then a more low level entry point. So if you're just a casual audio developer, you might want to use this easy API. And if you want to, you know, have more low latency, need a bit more fine tuning, you would use this low level API. And then there's a bunch of other common API calls. And I'm really only going to focus on this low level one because I find this more interesting and more intriguing. So let's talk about sort of the key API stages when you're interacting with audio devices. Probably anyone who's done, you know, directly outputting audio to a device will know, well, you know, when you want to start doing audio, you sort of have to open the device. So you need to say, oh, which device do I actually want to talk to, right? Is it my USB device? Is it my built-in audio device? Then you normally configure the device. You would say how many input and output channels, what's the sample rate, what's the sample format I want to use, what's the buffer size. Then you start the audio device. And when you start the audio device, your OS will normally give you regular audio callbacks, right? And then you stop the device at one point when you're done doing audio and you close it again. And in this section of the talk, I just want to focus on these audio callbacks, right? So an audio callback, the operating system calls an audio callback in your app, and you're expected to fill a buffer of audio with the samples that you want to play back. That's the APIs we're used to. Now, surprise, surprise, in ALSA, there are no audio callbacks. So that's a huge difference compared to any other audio APIs that I've seen. And to understand why, let's kind of look at a more detailed look of, you know, how we think, or, you know, how audio hardware works in essence. So your typical audio hardware, you have your device, you have your CPU, and then they share an audio buffer together, right, to communicate with each other. And this audio buffer has an application pointer where sort of the CPU writes in the audio that it wants to play back. And it has a playback pointer, often called the DMA pointer, where the audio device reads out the samples from this shared buffer. And at the beginning, when you start playing audio, or just before you start playing audio, the application will fill this audio buffer with audio that it wants to play. And the playback, the device will sort of, start playing samples, and this playback pointer will, increment one by one by one by one while it's playing audio, right? And it keeps on doing this. And, at one point, maybe the application pointer will start refilling this buffer. And when it gets to this end here, something very important happens. It does two things. It wraps around. So the pointer goes back to the beginning, but it also triggers an interrupt. So it wakes up the CPU to saying it, hey, you got to do something, you got to process some more audio. So that's sort of our general idea of how to do audio. And by the way, questions, I guess they're in the chat. I don't know, Josh or Timur, as I don't see the chat, just please relay any questions.
Yeah, exactly. So just if I can briefly say something, feel free to ask questions on the chat in YouTube. And also when you do so, please prefix them with question in all capitals so they're easier for us to spot. And then what I'll do is after you talk, I'm just going to read them to you.
Okay, great. But you can also interrupt me during my talk. That's also fine.
Oh, okay. If you're fine with that, then
yeah, sure.
I'll monitor the chat and we'll do so if it's appropriate.
Okay, great. So ALSA being a very, needing to run on embedded systems in all of these markets, as we saw before, has very, close, very low level, close view of the device. So what ALSA does, it doesn't have audio callbacks. It actually maps the device's audio buffer into your own app's memory, right? And you can directly write into this buffer. You can also ask ALSA what that current position of that DMA pointer is so that you can synchronize your writes, right? So how does this look like sort of in practice? You start, in your audio app, you start the audio device. Then you ask ALSA, hey, what's the current DMA position? And then from that DMA position, you check if there's actually room to write audio. And what I mean by that is, imagine you're in this situation here, you've already written 4 samples into the audio buffer, but in the meantime, the playback pointer has already moved along, right? It's already played, I don't know, here, 10 samples or so. So there is, 10 samples of available room for you to write into this audio buffer. Okay, let's say, but this is not the case. If this is not the case, well, you just go to sleep again, wait a few microseconds, wake up again, you check the DMA position again. Is there now room to write some more audio? If there is, you write your audio into the DMA buffer, sleep, and then you go around and round and round in this loop. Now, ALSA doesn't do it quite like that. So this would be like sort of the super, super, super low level. And ALSA does a tiny bit of indirection, but only a tiny, tiny, tiny bit. So you don't get this DMA position directly, but you actually get how much room is left in the buffer. That is what ALSA gives you, right? So ALSA keeps track of the application pointer for you, like how much you've already written into the buffer. And this is really, really good because that means your app doesn't need to, keep track of if the pointer is wrapped around already or not. There's like some ambiguity there, and ALSA will do this for you. So all you do is you just ask ALSA, is there room for me to write and how much? So sound PCM avail will return, 10 samples. That means there's 10 samples of room for you to write into that buffer. Also, you cannot quite access that DMA buffer directly. You need to lock the DMA buffer when accessing it from user space. So before writing into it, you have to lock it. You do this by calling PCM mmap begin, and that will return a pointer into the DMA buffer for you. But that pointer will already have that application pointer offset applied for you. And when you're done using it, you call sound PCM mmap commit, which unlocks the buffer.
So Fabian, there is a question from
Yes.
Ivan Smith, who's asking, what's the typical size of that buffer?
That, because we have such a huge market, it's really like on desktop, it would be the same size as you have on core audio, which is, I don't know, it could be 256 samples up to 2048 for 4096. It's the thing you can usually, set in Logic or in Pro Tools. That would be, on a desktop machine. On an embedded machine, it might be much, much larger, right? Because you want the overhead of these interrupts. But we'll come back to that a bit later. But I mean, those are sort of the typical buffer sizes you get. But it kind of depends on which device you're running on. So how would this look like in code? You would call sound PCM start, which starts your device. Then you enter the audio loop. You ask ALSA how much room is available in my in the audio buffer. Then you lock the audio buffer. That returns a pointer and the maximum amount of samples you're allowed to write into that buffer. That will become clearer in just a second. Then you call your audio callback to fill that buffer with audio, and then you unlock it again. And then you sleep for a few samples, and you do the whole thing again. Now, there's a slight problem, and that's if you're at the very end of that audio buffer. So let's say your application pointer is 1 or 2 samples before wrapping around. Now, there might be more samples available than just those 2 samples, but that means you'll have to wrap around. So this is why this map begin returns a max samples, because what you have to do is call this in a loop 2 times, maximum 2 times, right? Because if you're in this situation, then the first call of map begin will give you sort of the offset up until the end of the buffer. And then if you loop around the second time, it will sort of give you the offset from the beginning of the buffer to where the actual DMA pointer is. So there's a slight indirection needed to be able to cater for this case where you're at this sort of wraparound point. And that's why this PCM mmap begin returns this max. But if you loop 2 times, you'll always have consumed these n number of samples. Sorry, I just have to cough. Let me mute my audio. Okay. Now, this sleep might be a bit strange to some, like this kind of random that you just have to sleep a few samples. So ALSA provides another call, which is called sound PCM wait. And that sound PCM wait will wait for that wraparound interrupt to occur. That means whenever sound PCM wait unblocks, so when you call it, it will block until you get that wraparound interrupt. And then whenever it unblocks, you will always have at least a full buffer size of audio available. And now if we look at this audio callback again, well, if you just look at it at the point of view of the audio callback, it's not that much different to core audio or Wasapi, right? This audio callback is being called regularly, and it will always be called with a full buffer size of audio. And so you might really ask, what's the point of this, right? Like, why do I have this extra overhead of needing to write this loop when, the result is basically the same? We're just calling an audio callback in regular intervals. Well, let me look at this example. You have an aggregate device, right? You have an aggregate device. You want to do audio with some kind of capture device and a different playback device. And let's just say they share a clock externally via, I don't know, some BNC cable, some master clock, or whatever. Now, if you were to do this on core audio, you would need to open the capture device. And for the capture device, you would be receiving audio callbacks on a real-time audio thread, number 1. That will deliver you n samples of audio. And now what you would really like to do is just pass this on to the playback device. But you can't do that, right? There's no API in the core audio stack to just say, hey, play these samples. You can't do that. So what you have to do is you have to do something with these n samples, right? So, well, you just put them in a ring buffer. And then on a separate thread, your playback device will get an audio callback, and it can take out those n samples and play them back. But this is a bit wasteful, right? We have this buffer in between. So here you can see why this API makes sense, right? And ALSA, what do? Well, you just open both devices. You wait for n samples on the capture device. And when there's with the sound PCM wait, for example, and when there's n samples available, well, you just copy them over to the playback device. Done, right? There's no extra threads involved or extra buffers involved in this ALSA case. Now, in code, it's very simple. You see, we're just starting both devices, then we call wait on both devices. And, just to be clear, let's say you wait on the capture device, right? But the playback device has a full buffer size available before the capture device has a full buffer available. that doesn't matter because we'll wait until the capture device is a full buffer available. Now we go to the playback device. The playback device already has a full buffer available. So that second wait will just be a no op. And then we calculate how much is actually available. And then we just lock both audio buffers and we just copy over the data. And just, asterisks here, I'm ignoring this sort of DMA buffer wraparound that I showed before. We need the 2 loops. So I'm simplifying the code here a bit in ignoring that case. In real code, you would need to have two sub loops here to sort of deal with that case.
There is one
And
question
now I
from
want to show you another example, which is very similar, but instead of these devices sharing a clock, these devices are running on separate clocks, right? And now in core audio, how would you do this? Thread 1 would be getting an audio callback, right? And it's getting n samples from the capture device. But because they're running on different clocks, we have to run this through an ASRC, a sample rate converter. And the sample rate converter will deliver m samples, right? So a different number of samples. Now this will go into a ring buffer. And now on thread 2, on the playback device, we get a callback, but the callback is requesting n samples again, right? But we only have m samples. So this is always a problem with aggregate devices on core audio or Wasapi or Juice, is sort of this mismatch. And the only way to get around this mismatch is to make this ring buffer sufficiently large, right? Because it will even out in the end, because the rate of callbacks on thread 1 will if m is bigger than n, then the rate of callback on thread 1 will be lower than the rate of callbacks on thread 2. So if you average that out over a long time, it will work out. There will be no underruns, but you have to average it over a long time. So that means that this ring buffer has to be really large in this case. Now the nice thing, and that of course introduces latency, right? Making this ring buffer larger. So the nice thing about ALSA here again is not only, is this all in one thread, but it doesn't matter how many samples we deliver to the playback device, right? So we can wait for n samples on the playback device. That gives us m samples, and we can just push the m samples into the playback device. The playback device doesn't need an exact amount of n samples. It can happily deal with m samples. So this is just an example to motivate why this API is really, really nice in this case. And this totally makes sense for the use cases on Linux, right? If we think about this API on, let's say, embedded systems, which have very low memory, don't have much memory, accessing the sound card buffer directly means we don't have any other audio buffers that we need to allocate. You create and set up the audio thread, right? Unlike on core audio or Wasapi, in core audio or Wasapi, the audio thread is sort of given to you. You just get an audio callback on some thread, but you don't know how that thread has been set up. You don't know the thread's priority. You don't know if it has some kind of core affinity. And this is super important on embedded systems, because in embedded systems, you want the cheapest CPU you can find. So you really want to, tune your algorithm, and you want to spend a lot of time tuning your algorithm so that you can afford to have a cheap CPU. And some of these things you want to tune is, for example, on which core will the audio thread run? What is the thread priority? And you want to reduce the amount of threads you actually have. And this is super important on low power devices, on mobile. The problem with having many threads is that they're all scheduled to wake up at different times. Now, even if they were scheduled, let's say, you have 8 threads and they all roughly wake up every 10 seconds, let's say, right? But they only roughly wake up every 10 seconds. So one wakes up at, 10 seconds and 10 milliseconds. The other one wakes up at 10 seconds and 20 milliseconds. Now, let's say the algorithm doesn't care if it's 10 or 20 milliseconds apart. It would be okay to just all wake them at 10 milliseconds, but the operating system has no way of knowing that. So it will have to, at the 10-second mark, we'll constantly have to wake up the CPU completely unnecessarily. And with ALSA, we can have several devices all using a single thread so that we don't have this constant wake up. So this is super important for mobile. And then we saw just this broadcasting case, right, where you have several devices that you want to sort of aggregate into one. This is a very typical use case in broadcasting. So, the ALSA audio API allows you to do this with low memory and low CPU overhead, but also with low latency. Okay, so that was sort of the main audio callback and how ALSA deals with this. And now we're going to talk about some of these other steps in the audio API. So let's talk about opening a device. Now, Core Audio or Wasapi, you open a single device for both capture and playback, right? You get a single callback for both capture and playback. And what typically is done is that the callback delivers you the input audio, and your app replaces or outputs the playback audio in return. And this is this is also what's kind of happens in hardware, right? You have a single audio buffer, and sort of the capture audio is replaced with the playback audio. And this is super low latency because, in the same callback where you're dealing with the capture side, you can add, for example, an effect to that captured audio, an echo or whatever, and immediately output it again. ALSA doesn't work like that. ALSA only allows you to open the device either in capture or in playback mode, never in both, right? And that might seem strange and problematic for this low latency audio that I just mentioned. So let's look at this more closely. In ALSA, let's say you have a single hardware device that can do both playback and capture. Now, as this is presented into your app, though, it's presented as two completely separate devices, a capture device and a playback device. Now, we saw in the previous slides, this is not such a huge problem because, we can use a single thread for this, right? We can just wait for end samples, we capture them, we process them, and then we just copy them to the playback buffer. But there's a slight problem with this, and that's is the way these two devices are started, right? So this works, but imagine we're starting the capture device first, and then we try to immediately start the playback device right after with these two sound PCM start calls. The problem is, between those calls, your OS might decide, oh, I need to go fetch some memory, or I need to swap out some memory, or I need to do some garbage collection of memory, or an email just came in. And so there might be an unknown time between the capture device started and the playback device started. And this just means that you need to make the playback buffer sufficiently large that sort of the DMA pointer can have already advanced a few samples before you actually can mem copy stuff into that. But this,
Fabian, there's a few questions about this. If you said
right.
I'm okay to interrupt you, so I'm just going to.
Totally, yeah.
So first of all, could you go back to when you had the core audio, the threads, the multiple threads?
Yeah. Mm-hmm.
So there's a question from Euglosine Forever asking, does core audio add the threads together starting at power on?
Add the threads together on power on. I'm not quite sure what he means with power on. I mean, there's something I'm hinting here at is that, of course, Core Audio will try to make an effort to combine these threads, right, if it can. For me, again, this talk is more about the API as that as a user, you do not know if this is on two separate threads or not. And when programming with Juice, I would say that most times it did come on two separate threads. Yeah. And sometimes I saw it come on a single thread. The thing is sort of, you don't know, right? And I'm sort of showing you the worst case here, but I'm not sure if that's actually the question that was asked.
I think the question about the power on, correct me if I'm wrong, I think the thread is probably started when you start the device, right? At that point.
Right, yeah, right.
And then
or maybe when it's
what is going to be on, you basically don't know, right?
Exactly, yeah, exactly, yeah.
Okay, yeah, I think that makes it clear. I hope that answers the question. Otherwise, please, tell us on the chat if it's not been answered. And there's one more question about what you were just saying from Joe Noel. Asking, if you don't write to the playback buffer regularly, what do you get? Do you get silence or do you get junk?
It will underrun. It will basically stop playing back. So ALSA will just return error whenever that happens. So ALSA will automatically stop the device, or usually in hardware, the device is just stopped. And then ALSA will, on the next time you do any call, API call, it will return error and tell you that your device is underrun. This is, different to Core Audio. This is very low level, and certainly also in Core Audio or on Macs, devices can't when they underrun, they stop immediately. Now, what core audio adds on top in a very, very low level is that it will always prevent that from happening and adding, zero out the buffer, so you get these dropouts, right? But again, as ALSA is very, very low level, it kind of keeps that up to your user app. If you want your device not to stop in this situation, you need to, ensure that you just write in zeros when that happens.
So
Sorry, it's a very complex answer.
Whatever is in that buffer, right?
Well, no, but that's not normally how hardware works. That's normally what we see in software, but actually in hardware, most hardware, the hardware will in itself detect an underrun and just stop playing. That's how most hardware works. And what you usually see is when it just keeps on replaying what's in that buffer, that's usually a software thing, because on a very, very low level, there's something always, very, very low level, there's something always copying data into that buffer. And if that buffer from where it's copying from is not updated, then you will get sort of this that it keeps on playing the same audio over and over and over. I was surprised by that as well.
I did not know that. This is really interesting, because I always stopped at the level where you get this callback, and I don't really know what's going on in all, even lower levels. So
right.
Well, that's super interesting. Yeah, that makes sense finally. Thank you.
And that will also come in a bit later in the talk. Will become a bit more clear. Yeah.
Oh, okay. One more question. Sorry. So Leo was asking, so in the audio loop, if you wait for the wraparound, doesn't this create problems, as you don't necessarily have the same length of samples until the buffer's full, so not a periodic call?
Yes, exactly. That's a very, very good thing. Very good question. And so if you look carefully, I don't want to go back all the way because I'd have to see the arrow all the time. But if you look carefully on the code, I actually checked how much is available, but then rounded down to buffer size, right? Because I know that the sound PCM wait will wait until at least a buffer size is available, but it can be more, right? And so this avail might say, oh, there's 514 when the buffer size is 512, but I round down to 512 so that my audio callback will always be called with the same buffer size. But I wouldn't need to do that, right? And then you would have for 514, so there's 510. That's what you would get, yeah.
All right, thanks. That makes sense.
Okay, so simultaneous playback and capture. So the problem here was that this works, but that the starting time of the capture or playback device, there can be an unknown time offset between that. That means the playback device, the DMA pointer could have already moved in time, let's say 10 samples, until the capture device actually started. And this means that when it's time to write these n samples, you need to make sure that the buffer size is n plus 10 at least. And this is bad because this increases latency because we have higher playback buffer sizes now. So to avoid this situation, ALSA adds an interesting API call called Sound PCM Link. And Link links any two separate devices. And when two separate devices are linked, the only thing that will happen is that a single PCM start call on any of the linked devices will start all of them as closely in time as possible, right? And this as closely in time as possible is not guaranteed. Yeah, it's only guaranteed to be simultaneously exactly if these two devices share something called the same synchronization ID. And you can query the device's, any device's synchronization ID via another call called sound PCM info get sync. And so let's say you're using the same hardware device, right? In software, it looks as two separate virtual devices. You query their synchronization ID, they'll have the same synchronization ID. So when you link them, you know that that single sound PCM start will start them at exactly the same time, right? Because it's the same hardware. They start at exactly the same time anyway. But this is a very flexible API because this allows you to do much, much more. Well, first, what's nice about this API is that the app code, that your app's code doesn't really care if the capture or playback is the same device or a different device. It will always look the same, right? Even if these were on separate hardware devices, you want the start to be as close as possible together as possible. And this is what this link will do. It will try to, start both devices as close as possible. With the synchronization IDs, you can now do buffer optimization. If you see actually, oh, they share the same synchronization ID, then you would choose a smaller buffer size, right? You would decrease the latency. If they have a different one, you would increase it. Yeah, here, sorry. Querying the synchronization ID allows to optimize the buffer sizes so that the latency is just as good as in core audio. In addition to this core audio, though, the ALSA API also supports linking more than 2 devices. So you can technically link 5 devices together, and there could be some other means of synchronizing these 5 devices, even if they're not the same hardware, right? Now, I can't think of anything, but maybe in broadcasting, there's maybe like a trigger clock or a trigger signal that goes out to all of the devices, which makes them start all at the same time. So this is something that this link API can do, which, for example, would never be possible in core audio, because core audio only gives you a single callback for the same device, and only, you only have capture and playback. You don't have, 3 captures of 3 different devices and 5 playbacks of 5 different devices. So this is kind of a neat trick. Okay, so that was the open stage. Now let's talk about this configuration stage. Now, typical audio configuration, you set how many channels you want, the buffer size, the sample format, the sample rate. And on desktop, really, all of these parameters are usually completely independent from each other. And, just case in point, core audio has this call. It gives you a list of the nominal sample rates. So an audio device would say 44.1, 48, 96, whatever, right? And now the result of this call would not depend on if you've already said, oh, I want 8 channels, or I want, I want 16-bit. The result of this call will always be the same. And this is super problematic on mobile because, or even on embedded. Normally the CPUs, I wrote SoCs here, so system on chips, they usually have sort of a maximum audio buffer size that they can support, but this buffer size is in bytes, right? So if the sample size varies depending on the sample format or on the number of channels, your buffer size in samples will depend on that. Often mobile SoCs also have an upper limit of how many times this wraparound interrupt frequency can be generated, or they just have a maximum limit on the audio bandwidth, on the amount of data that can be sent to the audio device. This means now that all of a sudden the buffer size and the sample rate depend on each other. And then very, very common on mobile is that the codecs support compressed formats natively, right? This is really important that you get these, 10 hours call time. And that's only possible because the underlying codec supports, the compressions that's used in telephones. But these compressed formats often have a very complex dependency on, for example, the selected compressed format and the number of channels. Just think of MP3, right? MP3 can only be mono or stereo. It doesn't matter if your hardware would support more. The format MP3 has this limitation.
So Fabian, now that you're talking about mobile specifically, can I ask you a question here?
Sure.
So, one other limitation on mobile platforms, like for example on iOS specifically, is that you don't actually even get access to the audio device at all, right? You have these like sessions,
right.
which basically just say, your app wants to output this kind of audio on whatever the output device is, and then you don't get even to choose things like, if the user plugs in their headphones, it's going to switch to the headphones and stuff like that. You don't even have this kind of low-level stuff. How does this square with like you talking about like such a low-level thing on mobile?
It doesn't, right, is the answer. And the only mobile only the mobile platform which uses Linux is Android, and Android does use ALSA under the hood, but it doesn't allow the apps to actually access that. So, this talk is not about the, I might have lied a bit at the beginning of the talk. Good for pointing this out, actually. I didn't think of this, but my definition before of a low-level API was that a user app is the lowest API that a user app could access. On Android, that's not true. On Android, you cannot even access the ALSA API. The lowest level API on Android would be OpenSL or the Java.
And the same thing is true for iOS, where you have the core audio HAL, which is kind of of low level of device,
Right.
but in iOS you cannot access that.
Exactly,
So
exactly. So this would be for sort of, I mean, this talk would be for Android developers, right? Because Android developers are using ALSA directly, right? So Android system developers, sorry, not Android app developers.
And on the Apple side, it would be like the core audio team.
Right, exactly. Yeah, totally. Yeah, that's a really good point. Yeah. And again, I mean, this talk is what, I mean, why I wanted to give this talk and what I found fascinating is I learned so much about how the hardware works when, finding out how to use ALSA. And so I hope this talk is still useful, right, for Android developers, because it just shows you how the hardware actually works under the hood.
So now that, I have you in between two slides, I can just sneak in another question from Michelle Picaro. I hope I'm pronouncing that name correctly. With this low-level access to hardware audio, what are the performance on latency?
It's good, right? I mean, let's put it this way. Any other API, like a core audio type API, would be a wrapper around these low-level APIs. So any other API can only have equal or worse latency. Right. It cannot have lower latency somehow. That would be magic, right? So I mean, this low-level API gives you the lowest possible latency, right? That's the only way I could answer that.
Mm-hmm.
Yeah.
All right, thanks.
So yeah, the configuration on mobile is really, really complex. And for ALSA to cater to this, ALSA has this concept of a configuration space, and I really like this idea. So a configuration space is sort of these parameters that we saw: buffer size, sample rate, channel numbers, etc., format. They sort of span a 4D space, right? If you think about it, and ALSA constantly allows you to probe the edges of this space at any given time. Okay, this is really complex, so we need some diagrams, right? So I'm just going to boil this down to 2D space. Let's just say the only configurations you could do would be sample rate, number of channels, because I don't want to have a 4D graph on this slide. So at the beginning, when you open your device, you start with the full configuration space. Yeah, you call this API called, say, hardware params any. That means that will give you the full configuration space. And here in this example, right, as the number of channels increase, maybe this is a bandwidth limited device, the maximum sample rate comes down, right? But any point in this yellow area is a possible configuration for your device, right? So you could choose a low number of channels and a really high sample rate. And you can probe the extent of sort of this area with API calls. You can say, what is the maximum rate that you can get? What's the minimum rate I can get? What's the minimum channels I can get? What's the maximum channels I get? And, to be clear, this only gives you the bounding box of this configuration space, right? You don't see that there's a space you cannot access, right? These calls give you sort of the limits of these parameters. And what you then do as a user app is you start to constrain this space. So you say, well, my app needs this minimum number of channels. And now suddenly you've sort of constrained this configuration space to only the right side. And that means that the maximum rate now is lower, right? Because if you look at that right area now, for which we constrained our space, the bounding box of that area is now smaller, right? And you continue doing this. You say, okay, well, in this space, I would now like to use the maximum sample rate. So now all of a sudden, you've collapsed the y-axis to a line, because now you know which sample rate you want. And then you start collapsing all of the other parameters until you only have a single point left. And that's when you've chosen sort of your configuration. So I really, really like this design because, first of all, it allows you to navigate this really complex configuration dependency space. But what I struggled with, and you can look at this in the juice code, with this plethora of devices that are out there, if you look at the juice code, like when we sometimes open a device, it does like this dance of like, well, to me, it's important that like my sample rate is above 44.1, but what it really is, I don't care. I just want the max sample rate. But, core audio can't know that. So you're kind of doing this thing like, well, I'll try these channels, I'll try this sample rate, and that is just a really bad way of doing this. With this ALSA API, you can tell, the API, I need a minimum sample rate of 44.1. I don't care what's on top. Or you can say, I need exactly 48 kilohertz. And now what kind of channels can you give me? So that's a really, really cool API. And now only left on this diagram is stop and close. And I'm not going to talk about that because they're boring and they're the same on any API really. So we'll just skip that. But I want to talk about something else. And that's, I've always used this term buffer size. And what is a buffer size actually? I mean, let's look at this audio buffer thing again, right? We have our DMA pointer. And this DMA pointer slowly increments until it reaches the end. And only then it wakes up the CPU and then it wraps around. But that's a bit strange, right? Because if it only then wakes up the CPU, how on earth can I do in an instant, I would have to deliver audio, right? So I basically in an instant have to replace the old buffer with a new buffer. And then the playback can continue because the playback pointer has wrapped around. It's expecting new samples now. I mean, one way to solve this, and I'm not saying this is how Core Audio or any of the APIs solve this, but like one way to solve this is you have another copy of the buffer in system memory, right? Not even related to the device. It's just another copy. And your audio callback only ever operates on this copy. So your callback can now take a long while to process because it's only processing on the copy. And every time this thing wraps around, you basically just instantaneously copy with a mem copy, for example, or a burst. You basically copy this buffer over to the other. I'm only talking conceptually here, right? Like this is not how hardware works or not, but this is a concept in software development and also with certain hardware. Which is often called double or triple buffering. But this is really confusing now because what do I mean with buffer size, right? If we look at, we have kind of two sizes here, right? We're increasing the latency because we now have a total buffer size of 2 times this buffer size, or 3 times if we do triple buffering, right? We're increasing the overall latency of the system, but the size of the buffer supply to the callback stays the same. Right, so we have kind of 2 callbacks here. One is sort of this, the total buffers of where audio can be, but then you also have the size of the buffer that your audio callback gets. And so this term buffer size is super vague, and people use it in all sorts of contexts, and you never really know what they exactly mean. And this is nice with ALSA because it clearly, totally distinguishes between 3 terms: buffer size, period size, and FIFO or block size. So in ALSA, a buffer size is always the complete total buffer size of your system, right? All of the buffers in your system. And now there's something called the period size. And this now means that your buffer can be subdivided into several periods. And this is how hardware actually works, right? So here I've divided my buffer size into 4 periods. And now with every period, I'm getting a wake-up call, right? And this is the hardware will produce an interrupt every time I go from one period to the other. And this is, if you think of the sound PCM wait that I had before, every time sort of a period elapses, this sound PCM wait unblocks. This means that every time the sound PCM wait unblocks, there's always a period of audio available and is ready for processing. But when a period of audio is available, there's still plenty of other periods to play, right? As you saw in that diagram, there were 4 periods. So when there's a period available, there's at least 3 other periods for the audio device to play. So there's no underruns. And this period thing is that period size, that is what is sent to your audio callback. So in ALSA, you will always see, like when they talk about like higher level APIs and the callbacks, they're always talking about period sizes of buffers being sent to your audio callback. And the buffer size is sort of that full block of audio. And this buffer size, as I said, that can be divided into several period sizes. And the number of periods in a buffer is sort of this double or triple buffering, right? Or quadruple buffering, or whatever you want. Which, for example, is a term in Wasapi. In Wasapi, you can actually explicitly say if you want double or triple buffering. And this is equivalent to this. Of course, you must have at least 2 periods per buffer, because we saw in this case before, if you only have a single buffer and it wraps around, there's no way for you to instantaneously generate audio when the CPU has been woken. So you always need at least 2 periods of buffer, always need 2 periods. With the exception that ALSA, of course, also allows for 0 periods, because we see you don't need to use the sound PCM wait, right? You could just sleep. You could just say, oh, I'm going to sleep for a few samples, or you could be relying on a sound PCM wait of another device to wake you up and then write into that. And if you don't want any interrupts coming from your device, you can actually turn them off altogether and just say, I don't want any periods, right? I'm going to rely on some other mechanism to wake up the CPU. And then we have FIFO size or block size. And this was completely new to me. This kind of blew me away actually when I saw this, because I've been doing audio for 20 years and I always assumed that the hardware sort of increments, right, in samples, right? So that the device has an audio buffer and it will sort of, while it's playing, read from this buffer. And that's wrong. Maybe very old sound cards did it this way, but this is not how it works today. And you can kind of understand why it doesn't work like this if you ask yourself where this audio buffer is actually physically located. So there's 2 options here, right? You can put the audio buffer inside the actual audio device, or you can put it into the system RAM. And if it's in the audio device, sort of the CPU, whenever you're doing audio processing, will sort of have to will have to sort of copy or write or process audio on this audio device. And if it's in system RAM, the audio device will always have to access the system RAM when playing back or capturing. And both of these approaches have downsides. If it's inside the audio device, well, you need extra special RAM on the audio device for the audio buffer. And audio buffers tend to be big, right? So that's expensive. You would want to do this maybe in SDRAM, but SDRAM is super expensive. And DRAM, well, you could do DRAM, but a DRAM, then the buffer is too small for DRAM, because DRAM needs an extra controller, a memory controller, and all of that overhead. So that's also not really good. And we have a huge RAM sitting right there. But the downside of using that system RAM is that the audio device, think about it, it's playing, it doesn't have any other memory. So it has to always, every time it wants to play back a sample, it always has to access the system RAM, every sample. So every 20 microseconds, it's accessing the system RAM. And, especially a mobile, that would be super, super wasteful, because, accessing the system RAM is not straightforward, right? There's a DMA controller in between, then you have a RAM, sort of RAM, you read and write RAM in sort of in cycles, right? There's a refresh cycle and all of this stuff. So, waking up the DMA controller to read out of system RAM every 20 microseconds would be a no-go on mobile. So the solution is to actually have a buffer in both the audio device and its system RAM. So you have a smaller buffer in the audio device, you have a very large buffer in the system RAM, and this audio buffer in the device is often called a FIFO. I mean, they're both technically FIFOs, but that's like sort of, if you look at literature, it's usually called the FIFO. And the FIFO is typically small because memory is expensive. It's normally like 32 to 128 samples. It depends on the sample format and number of channels, of course. And when the FIFO is half empty, the audio device will go fetch a block of samples from system memory to fill it up again, right? And this means that this idea, what I had, that this DMA pointer that we see from user space, that it sort of advances in single samples is not true. It actually advances in this block size, these block sizes. And ALSA allows you to query this block size and the FIFO size. And so just as a recap, the buffer size is the actual size of all of the buffers in total in hardware. The period size is the number of samples after which the CPU is always woken up to do some more audio processing, or another way to say it, it's sort of the buffer size of your audio callback. And the block size is the number of samples that the audio device reads and writes from the audio buffer in single bursts, right? And your latency can never be lower than this block size, right? Because by hardware, there's some internal buffering going on that's at least the size of this block size. And this block size, by the way, is not always fixed in every hardware. So a lot of hardware, this block size can vary depending on system load, etc. So this brings me to the last part of my talk. Timing is everything. I want to go back to this use case that we saw before, where you have a capture device, you have a playback device, they're running on different clocks. And so when you're doing this aggregate device, you need to have some kind of sample rate conversion in between. And when we showed this before, I said there has to be a large ring buffer in between them to sort of compensate for that. But there's a key question is like, what informs the sample rate converter? Like, how do we get the rate for the sample rate converter? And if this is not accurate enough, then the latency will be very, very high because, sorry, let me just clarify this. I mean, if as we saw before in the other slides, if we need to average over many, many callbacks to get a good rate, that means that the ring buffer between these two devices has to be super large. And that means we increase latency. So sort of legacy devices, how to actually, so key here is to determine what rate the capture device is running at and what rate the playback device is running at. And then divide those two rates, and that's the rate you want to run your sample rate converter. So it's key to understand at what rate your devices is running at. And I wrote sound drivers back in the day for Behringer and for Creamware. That's why on the left, this icon that you're always seeing is actually a Creamware device. And back then, the timing by the operating system was done the following way. And I've always thought that this is still done today like this. Is we said that when the DMA pointer wraps around, it wakes up the CPU, right? It generates an interrupt. When the CPU is woken, at least back then, it would take a snapshot of the system clock, right? It would say, what time, currently, what time of day is it currently? And if you divide sort of the size of your buffer by the time it took to actually play that buffer, because you have these clock snapshots, well, that gives you the playback rate of the device, the actual playback rate of the device, right? There's a nominal playback rate, which is 48K, but the actual playback rate will be something slightly different. This is not so good though, because especially on embedded systems, the interrupt jitter, the amount of time it takes for when the device generates that interrupt until the CPU actually is woken up can vary between plus minus 300 microseconds. So when you take that snapshot of that system clock, that will be varying a lot. Also, what's not so good about this is that the accuracy of how you calculate the actual rate will depend on how big your buffer size is. Imagine the buffer size is super large. You will only be getting sort of, you will only have an average of the rate over the entire buffer size. But the rate of your device may have changed during that buffer size. And that means that sort of for legacy devices, to aggregate them, to sync them up, you would require large ring buffers to average over a long time, and that would introduce high latency. While researching the ALSA API, which is very close to hardware, well, I found out that's not how modern devices anymore, precisely for this problem. What happens is, again, you have your CPU. Your CPU has some kind of system clock, and you have your sound device. And again, your sound device is running off some kind of external audio clock. And now key here is that the device has a counter of how many samples or how often this audio clock transitioned in state, right? Went from 0 to 1, from 0 to 1. So it just keeps track of that. Now, any real hardware device will be on some kind of bus, the USB bus or a PCI bus or whatever, on some kind of bus, and that bus is clocked. And on all hardware normally, that clock is the bus clock, which also clocks the system clock. So the sound card shares a clock, your sound device shares a clock with the system clock and your device. And so your device has another counter, which is the bus counter. That now counts how often the bus clock has changed its value from 0 to 1, etc. And now there's always some kind of register that you can read in the device, or some kind of a hardware function where the CPU can ask the device to take an atomic snapshot of those two counters at exactly, precisely, simultaneously at the same time. And that the device will send you that back to the CPU, and it give you this package of the two counters. And because the bus counter, the system clock runs off the same counter as the system clock, you can convert the bus counter to a system clock value. And now again, you can calculate how many samples have gone by in a certain time, and this will very, very accurately give you the device's actual rate. The nice thing is it doesn't depend on jitter, right? It could take a really, really long time for this transaction to happen. For example, it could take a really long time to read this clock snapshot package, but that doesn't matter. As long as the hardware took a snapshot of both of these counters at exactly the same time, that's all that matters. And also, it doesn't depend on buffer size, right? Because the CPU can take these snapshots at any point in time it wants to. And Core Audio, of course, and Wasapi, I'm sure as well, uses this functionality, but it kind of hides it away. It does some of the averaging under the hood. And when Core Audio calls your audio callback, it will give you a presentation timestamp telling you at exactly which time this audio will be presented. And that makes sense for Core Audio, because Core Audio is always callback based anyway, to give you basically the snapshot every callback. On ALSA, which is not callback based, right? You might not even get a callback for some devices. You might be sleeping, or you might be waking up your CPU due to some other device. You explicitly ask ALSA to get this snapshot for you. And this is why this is, again, closer to the hardware, and I learned how the hardware works. This is useful for callback-less audio loops, but it's also, as I said before, nice because it makes sort of this accurate rate calculation independent of the period size. In Core Audio, if you would want to make this rate calculation more exact, you would have to make the buffer size smaller. This is not the case with ALSA. That was basically it. That's what I learned about hardware and how low-level audio works. And so in summary, the things that I've learned is I always thought the only APIs out there are always callback based. That's not true. And when they're not callback based, it's actually quite good, because you can have variable buffer sized audio callbacks, sometimes 104 samples, sometimes 128 samples. You can create your own threads or reuse other audio threads. Then I learned that configuration spaces are cool, just because you can say that it's a 4D configuration space. It makes you sound smart. And then I learned how audio hardware actually works. So I learned the difference between buffer sizes, period sizes, and block sizes. And I learned that a way to synchronize different audio devices is that it's really important to be able to acquire these bus and sample counters atomically with these snapshots. So that's the end of my talk. Thank you for listening. Questions?
Thank you very much, Fabian, for this amazing talk. I learned quite a few things tonight. This is really cool. I mean, as you know, I've been doing audio for quite a while now, including low-level stuff like, we worked on Juice together and stuff like that. But quite a few things in here that I didn't know. And it was like, wow, this is how it actually works. So yeah, very, very helpful, I'm sure, for everyone who's listening as well. Thank you so much for that. We do have a few questions. So Kaushal Sali is asking, you had a slide where you had ALSA linked devices.
Mm-hmm.
You were saying that you can request a synchronization ID.
Mm-hmm.
And the question is, how is the synchronization ID assigned? Can it be set manually, or if not, like, who decides what the ID is? Like, how what is that?
It's like a UUID. ALSA generates it for you. To be honest, I think, as I said at the beginning of the talk, really, ALSA, the API as a concept is good. ALSA as an actual implementation is really, really bad. There's some really bad things about ALSA. And I think if I remember correctly, the way the synchronization ID is generated is basically just every driver has some kind of pointer in memory. And then because it's the same driver, it's the same device, that pointer is just translated to some UUID. It's like kind of, right. It's not so much about how actually ALSA does this as the concept of having these synchronization IDs, but yeah.
All right. So then Aura Audio is asking, when you're writing a program and you access the registers on the hardware, are they executed from the CPU and then sent to the hardware registers?
Okay, very good question. Yeah. So I mean, just to clarify, I mean, I don't think this is your question, but just to clarify, I mean, when you're dealing with ALSA, you never talk to the registers directly. The drivers, of course, abstract that away from you. So technically in Linux, you could go more low level because Linux is open source. Of course, nothing's stopping you in Linux to, change the way the kernel is written, that you could access the registers directly. You could do that. But with ALSA, you would, if we're talking about ALSA, you typically not do that. And well, just from a, hardware perspective, yeah, when the CPU accesses register in the device, it's just, it does this via like normal memory access, right? Like to the CPU, I mean, not quite in detail, but let's say on a high level, when the CPU accesses the register, it's very similar to just loading some values from memory. But I'm not sure, I feel like there was something else behind that question. Maybe you could clarify what you meant.
Maybe the person who asked that question can clarify on the YouTube chat. And while they're doing that, so there is actually a cluster of questions. I had one question where you said at some point when you were talking about that the audio buffer, there's like a separate audio buffer on the actual device, which I didn't know about. That's, wow, this is cool. And then you said, well, in the literature, it's called a FIFO. And I was just curious, like, what do you mean by the literature? Like, where can you read it?
No. I mean, this is, I just know that ALSA calls it FIFO. And if you read sort of all the CPU manuals, they always call it the FIFO. Right. So no, literature was wrong, right? I mean, literature is like sort of from I guess if you're a hardware engineer, you would call that the FIFO.
Okay.
Yeah.
Right. I guess there's like a meta question here as well about like the literature, because there's also two other questions. So Pierluigi Massapoli asks, where can we find this kind of deep documentation about ALSA? Like, where did you get your information from? And there's another question. Do you have more resources to learn more about the low-level parts, especially of core audio? So I guess it's a question about ALSA and core audio. Like, where do you get this information from? Where can someone find all that?
I mean, I think with terms of ALSA, this is what makes ALSA a very bad API is ALSA, there's very, very little documentation. And I mean, the problem is you have these, different API levels, sort of this easy API and the middle API, but the documentation doesn't really distinguish between them. Then you have tons of API calls. Actually, this get FIFO size or this get block size, no driver implements it. So it just always returns 0. So it's a really nice concept, but it's not implemented. But that's not written in the documentation anywhere, right? I found that out by reading kernel mailing lists and looking at the source code. I did some modifications to ALSA kernel driver. So I saw how everything works sort of from the other side. So I think it's a lot learning by looking at other people's source code, because there's very little documentation out there, sadly. With core audio, I think the situation is better. For sure, the sample code situation is much, much better. I mean, with ALSA, you just have to find open source projects, but Apple will at least push you in the right direction of good written sample code. And the documentation of core audio, especially the low level, is also extremely sparse. And I think it's because Apple doesn't want you using it, to be honest. And I think they're thinking about deprecating it maybe. I think Apple is going more and more to sort of limiting what you can do. And, I think wants to promote sort of the common APIs between iOS and macOS. So there used to be very good documentation for core audio, but that's more and more vanished over the years. I remember these big PDFs with hundreds of pages around core audio, and that you can't find those PDFs anymore. They're just gone.
Yeah, this matches my experience as well. When last time I was looking at the HAL, which is like the lowest level of core audio, like a year ago or something, it was always kind of still there. Like the headers were there, but they were like just the headers. Right. And like you had like basically the documentation was like the Doxygen comments above the functions if they were there, and then you were basically on your own.
Right. Yeah. Yeah. So. Yeah.
Yeah. So I have one more kind of meta question, which was actually asked quite early in the talk by Elanda Athena. but I thought I'll keep it to the end because it's like more like a meta question as well. So with like Linux providing such a powerful API, do you think Linux audio will get more attention in the future?
So I don't think so. And the reason is what I said is this interrupt jitter that I mentioned before. So let's say vanilla Linux as is, probably not. And the Linux kernel is not, the Linux kernel was invented for servers, and that meant was never intended for real time, right? Servers need a lot of throughput, but they don't really it's not a real time system. And those two things, they're kind of, you can't have both, right? You cannot have high throughput and have low latency, right? Because low latency means you have many context switches going on all the time, but context switches have overhead, which push down the throughput. And because Linux was made for servers, we want high disk reads and whatever, you normally traditionally want high throughput. So long story short, if you measure, if you look at the core audio stack, it has much better timing, much better. The interrupt jitter is very, very small. They have optimized this to the dot, where Linux was never made for that. There are real-time patches to Linux that make this situation much better. And if you look at people who have talked here before, like ALSA or some other people of the developers, they never use vanilla Linux. They always use a huge patch set on top of Linux to make this work. Unfortunately, these patch sets are mostly not compatible with ALSA. So when you're using these patch sets, you're not using ALSA. So I would rather, it's hard, right? Like for Sing, we're using Linux and we're using pretty much vanilla Linux. But there's so many advantages to using Linux being on an embedded device, low memory footprint. There's so many advantages. So it's a really big trade-off. Do you want to use vanilla Linux to get all of these other benefits, or do you want to use this real-time patch set, which will, now the support is much harder and things like that. So I think it's, I don't think Linux audio as such, Android is also struggling with it, right? Android's audio is never going to be good because, for security reasons, Android will never apply these real-time patches to the Linux kernel. They'll just never do that. So they're stuck with the Linux kernel, and you see it. The Android team they're intelligent. They're great people, right? They would have, if it would have been possible, they would have made the most awesome audio performance on Android, but they can't. So
yeah, this matches kind of my impression as well. Let's maybe wrap up with one last question, which I think is very fitting for this evening because, by the way, thank you to everyone who's watching this and not watching the Apple event, which is happening at the same time, where they're probably unveiling their ARM Macs right now. Right. And the question is related to exactly that. What does Apple Silicon mean? Or in your opinion, do you have any thoughts about what Apple's new hardware I am
so excited about it.
Low-level audio and high-level audio and making music software in general. What are your thoughts on that?
Yeah, I'm super interested in this because and the only reason is because, and I have to be, so I'm very interested in this because traditionally on Intel chips they were used for audio workstations. So the whole audio architecture and hardware, if you would get a sound card for Intel, it would always have this snapshot of these two clocks that I mentioned earlier. It would always have that because they know, well, it's on Intel CPU. You might want to do real-time audio, or you might want to do pro audio with this sound card, and so the hardware also, especially in Macs, any integrated Ethernet, for example, on a Mac will always have AVB support, right? That's required. That's a hardware change, right? And the Intel CPUs, they have special instructions for audio and whatnot. Now ARM traditionally does not have that space. So this, the last part of my talk where I said modern devices, I would say about a quarter of ARM SoCs have sort of this synchronization feature. And I can't go too much in NDA territory because I have a transition kit, so I'm not allowed to talk about that. But I'm very interested in getting a real retail hardware to see if what kind of audio chip is actually in that hardware. And I'm really interested, like, does the Ethernet still have AVB support? Like, I'm super interested in that.
Yeah,
But
you're on the same boat here. I think a lot of us have these DTK Macs right now, and
right.
we're waiting for the actual hardware. And you're
Right.
measuring stuff, especially if you do like low level, low latency
Mm.
stuff. What's the actual hardware going to be? And there's all these questions. And
I mean, in terms of just the CPU architecture itself, I don't think it matters. ARM, the actual CPU architecture, so the instructions and only the CPU part, not sort of the audio hardware inside the CPU. The actual only like the instruction part is as good as Intel, and that won't matter. It's sort of about the peripherals around the ecosystem that has been built around ARM and the ecosystem that is built around Intel to see what we're going to get there.
Well, so it's going to be a bold new world, which I guess we get to see quite soon. Right. So yeah, let's wrap this up because we've been talking for quite a while now. And I'm sure a lot of people want to see the Q&A with our other guests. So thank you again for this talk and also for all your insights on the questions, which were not all of them directly related to your talk, but you just have so many insights, in all of the stuff. So it's like really just learning. And I guess everyone is learning so much just from listening to you. So, thank you so much for sharing your thoughts on all of this. And I hope to chat to you soon. And
you too. And thank you for having me. It was a
stay
huge
around for the Q&A.
I will. Yeah.
Cool.
Okay.
And
yeah, thank you very much. Thanks for that, Fabian. So much conversation happening about it. There's a lot of interest in it. So thanks for your time there. And just a reminder, if you want to continue the discussion after this meetup, you can do it on the Audio Programmer Discord. You can join that through the audioprogrammer.com/community. And if you want to submit a talk and give a talk maybe on core audio or something like that, then you can actually do that by submitting a proposal at theaudioprogrammer.com/submit. So speaking of Apple, and we've actually got two guests with us that have actually done a lot of work on iOS, and and we're about to talk to them about their success with this and making a shift towards the other side of development, which is putting aside the code for the moment and talking a little bit more about product development. How do you make a successful product? How do you take these low-level concepts that Fabian has been talking about and make it into something that will actually sell commercially? So we have two people that know quite a bit about that. So we have Matthew Fetcher, who is the co-founder of AudioKit Pro and also the head of app development there. And he's been responsible for 7 #1 music apps in the App Store. So he knows a little something. Actually, he's lost count now. That's how successful he's been. And we also have Kennard Garrett, who has joined us. So Henny has had a last minute come up, so he's not able to make it. So his business partner, Kennard, has joined us, and he's from Westview Drive Production, which is a technology and education duo along with Henny. He's also a Grammy Award-winning producer. He's produced for Sting. I don't know if there could be anything more awesome than that. And he's also a multi-platinum producer and professor of music production at Morehouse, and also teams up with Matt to help him out on the concept for these apps. So thank you very much for joining me today.
Thank you for having us.
Yeah, thank you so much. It's such an honor to be on the show. And Fabian, your talk was really mind-blowing and so well done. So it's going to be hard to follow you.
Yeah, hard act to follow all the time. He does this to us. So great. So I guess one way that we could start off with is maybe just talking a little bit about AudioKit Pro and what AudioKit is. So there are people that may be familiar with it, but can you just tell us a little bit more about it?
Yeah, AudioKit Pro is an open source library, kind of like Juice, but more focused on iOS and Mac and Apple Silicon. And it allows people to quickly get up and running with music ideas for your apps, not just professional music apps, but kind of like simple things. As Fabian pointed out, core audio is very difficult to learn, and the documentation may have a few holes, to put it mildly. So we're just trying to educate and help, developers and would-be developers make apps. And as you guys all know, the music development community is mutually beneficial and circular, and we all like to help each other. So we're just trying to do our part to document things, especially newer technologies like AUV3 and other technologies.
Yeah, that's amazing. And let's talk a little bit further about some of your success in creating these apps. I mean, I guess the first question that many people may wonder is there a secret recipe, or how does that actually happen? How did you get your, I mean, there's about 5 questions in here, but how did you get your how did you get your path into AudioKit Pro, and how did you get kind of started towards this path of developing successful apps?
Okay, well, maybe it would be more timely to start with like our most recent one that we did with KG, and it really has a great story, and I think that kind of really helps if before you even start your app, you have like a great concept. So it's charitable. Money goes back to Morehouse College, where they can teach young people coding and music development and sampling. And it has 2 Grammy winners involved. KG is kind of a really big deal here, and it's been an honor to work with him and Henny and Jeff Cooper, who's an amazing developer. And it also has this education standpoint, where we did give away pretty much all the code for this app, and it's free and online on our GitHub. And we're still working on that, and it's a work in progress like anything. But I think it's one of those things you can't market an app after it's already done. You have to like build it into your product.
Yeah, so that's a really interesting concept, because you're talking about the process of, you have a developer or a number of developers that are sitting in a room with a computer working in AudioKit, and they say, okay, what do we make? How do we make something that people are going to actually use? And then on the other side, you've teamed up with KG and with Henny, and they're bringing their experiences. How do you put those 2 experiences together? Where does that process actually start?
Well, I'll let KG speak to this a little, but it's really refreshing because sometimes as a developer, you see like, your beta test users or like forums like KVR, and it's just like everyone has their own little opinion. But when you're working with, like a real artist, and they can sit down and show you how their workflow goes and say like, hey, well, as a developer, you have to put your ego aside and be like, hey, maybe I don't need this extra feature. I don't need all these extra cool things I can do. This is what a real working producer needs. Now, I'm sorry for talking so much, KG. I'll let you talk here.
No, it's all good, Matt. Love to hear your voice, buddy.
We all love Matt's voice.
He's got a radio voice. This thing for us was really organic, and Henny has been such a leader in the iOS music production space for years. We've known each other for about 20 years, and it's been amazing to watch what he's done in that space. And me just, having a background in technology, but of course a career in music, integrating iOS apps into my production workflow and recording has been one of those things I've always tried to be in front of, to make sure we as musicians are staying on top of the technology and how to create, not losing the foundational, aspects of music, but continuing to evolve as technology has made it easier for us to create and record. So working with AudioKit and Matt, it was really organic in the sense of when we met, it was kind of like, how can we figure out how to work together? And Henny and I were working on a couple of projects along with our teaching schedule of music production and recording sciences, and it just all clicked when we were, sitting talking about the syllabus, and we would be teaching things like sample rates and mic placement, mic selection, recording, all those things. It made sense to embark on something like this from an educational perspective, because all that's included in what we were trying to develop here, which was a recreation of a vintage instrument that I had sitting in the studio that we go to time and time again. One thing about it is, that's a 200-pound instrument, but to have the opportunity to be mobile with that, to have it at our beck and call anytime we wanted to create, as inspiration comes to us at many different times, anywhere. It was a dream come true. So that partnership started, like I said, very organically from the beginning. It was kind of like, how do we make an instrument that we would use, that we would, uh, value in our own workflow in music production? And a lot of great conversations came out back and forth in the development of what this should look like from a features perspective, but all the way down to UI. Like, what would I like to see as a user, um, working in this space musically? And it goes on to, what does the future look like for music and musicians, and how we integrate new technologies into our workflow to give us the results that we want.
And that
Yeah.
sounds like, yeah, go ahead. Did you have something to say, Matt?
Oh, I was going to say just like things that they taught me that I wasn't aware of that might help some other developers is, as a developer, we want to like add more things. Oh, I can add a flanger or a chorus just because I can, and it's cool, more, more, more. And then there's like, hey, just get out of the way and make it sound great so we can, use it on a record. Because working producers, they don't have time to go through 1,000 presets. They need a sound that sounds good right away. So.
Yeah, that's amazing. And it sounds like that creative process and that connection really, it reminds me of connections that I hear about with music creators, where it goes into something deeper than just, well, how do you create something that sells? It goes to something that really drives at the heart of both of you as creators. So can you talk a little bit about that more, about how this thing comes together, and and that you steer it more towards, sounds like you're steering it more towards, what is it that I would like to see, rather than, well, what's going to sell the most units, virtual units.
Yeah, I could start with that. So, from our perspective, as Matt said, we've been around keyboards, musical instruments, for most of our lives, and we wanted to just bring something into the market that really, as I said before, is something that we would use. And let's just take it from the simple idea of, how do we create, how do we make music, how do we write music. And throughout our careers, we've used many different instruments, that, we've actually got into the digital space, where it's become many virtual instruments that we use and we go to create things. So one thing that we wanted to do was just create a simple product. How can I take it back to the bare basics? So many times we get keyboards or synths, and we're looking at them, and it's like, whoa, that's a lot of knobs, that's a lot of stuff. I actually only want to use one sound out of this. It might be my go-to preset or go-to sound or tool, and then I want to integrate that with maybe 10 to 15 other pieces or instruments. And it's just like a typical recording session. I've got drums over here, I've got guitar over here, I've got bass over here, keyboards over here. And so we took that mindset, and when we approached this app, of making it simple, but as Matt said too, one thing for us, it can look great and it can have many different functions. But if it does not sound incredible, we've already compromised our creative process in doing so. So we took our time in sampling and making sure that the sound of the instrument was pristine. And thankfully, it just wasn't our ears listening to this, but we got a lot of musicians, touring musicians, other producers, people who probably were not as hip to the iOS platform or using these type of programs in their everyday gigging or touring or production. But we got feedback from them, real players. I think Henny and I both consider ourselves keyboard players, but we brought in some really incredible talent to battle test this thing, and make sure that it was up to the standard that they could take it on the road and they could use it in their live rigs or their studio productions. So, it's a lot of love that went into the development of it, but it really came from just, let's take it back to the foundation and build up from there. And it's kind of like music production in this sense, and maybe you guys see it in your world also. we got to know when to stop. And I think that's our job as producers. It's like, I don't need to add that extra uh, violin on this record because it doesn't need it. We got it there. We got it to the finish line. And so that's where we were trying to go with this app. Let's build it up to the point of we know where to stop, what's appealing to people who would use it. And let's keep it there.
Yeah. I had a question that's just kind of shifting gears a bit. So one thing that I've noticed in the audio programmer community recently has been probably over the past year, there have been more people of color, people that are outside the normal demographic of what we see in audio development of just kind of white middle-aged men in development. And I'm wondering, being of course on Morehouse, which is a mostly black college campus, do you see a trend of people that are getting more curious about music technology, audio development, and that side of things, and looking to get into this, particular sector of development? Because it's something that I've definitely tried to push in our community, but I'm wondering if there are ways that we can actually move that further.
Yeah, no, that's a great question. And that was one of the missions that I had and Henny has in coming back to Morehouse. I mean, we were both musicians and producers and have careers in other businesses, but it was so important because we're both graduates of the institution and we know the value that that college has played in our lives and the lives of many. We've got an incredible list of alumni, from Martin Luther King to Spike Lee to Samuel Jackson. But from a music community, we want to ensure that we came back to really empower these students about all aspects of music, not just being on the other side of the camera per se. Not only being the producers and performers, entertainers, and I think our love for technology. We are those gearheads. We are trying to find out what's the next tool, what can make my workflow better and my sound greater. It was important to impress upon them because I do agree with you. We don't see many people of color in this space, and for a lot of us, we are using products that are developed and conceived in the minds of people who might not traditionally use them the way that other musicians would use them. I think it's just a diversity in genre per se. So it was very important for us to be able to say, hey, look, guys, there is a market here, and you can be on the front end of development, which is key to the products and tools that you'll be using, even influencing how some of those tools are developed by the way you would use them. You can put, a synth or a keyboard in front of, 20 different people and you might get 20 different ways of using them. So, yeah, this is an incredible time, I think, for the music community, and through the use of something like AudioKit being open source code and iOS devices, which pretty much everybody has access to. We're making it affordable, attainable for them to even venture into that space. So, combining with the incredible Morehouse community and the incredible curriculum that we have around computer science and music, it is a merge between those two worlds.
That's amazing. And it's amazing to hear how these things are kind of coming together. Musicianship, technology, culture seem to all be converging for both of you, in the creation of these products. And one question I wanted to ask you, Matt, was just about in creating all of these successful apps. Do you notice what are some what would you say that there's a common theme that you have? Would you say that it's the theme that Kennard had discussed about simplicity and the communication with people that are actually going to be using these instruments, or is it something else?
Well, that's a good question. I almost feel it has a lot to do with platform and your community and building a following. And we're especially seeing it now during the pandemic, where things that you used to have to promote an app don't work anymore. Like, for example, you can't rely on Apple to feature it or get press. I mean, you still get press, and we're really thankful for any press that we get, but people just aren't paying attention. There's too many distractions. So, we've done a good job of like trying to be there for our users and, answer every email and, give more than we take. And, support people all around. And so like every time we release an app, hopefully, it's affordable and accessible and does the job. And I guess it's just one of those things where one of the best pieces of advice I could give for someone starting out now is to like build up their following, whether it be on platforms like social media and YouTube. Like Henny and KG have a rabid following on YouTube and Instagram, and that drives a lot of sales. And then we have a mailing list that's over 100,000 people, and that's just a huge sales driver for us because we're able to have a direct connection to our customers. And anyone who's dealt with the App Store knows you don't get access to your own customers unless you do it yourself. So definitely work on, cultivating that direct relationship with your customers, because if something like this happens, the situation we're in now, where all of a sudden there's no way to reach people, you just have to do it yourself.
And I remember a conversation that we had maybe about a year ago, actually, where you've been a mentor to me in terms of the direction of the audio programmer, where one thing that I think that any person that's in a creative process thinks about is, well, do you ring fence this product or this thing off, or do we offer limited access to something, and then we say, okay, but to get the pro package, then you gotta buy, or you gotta buy into this idea. And you had actually proposed the idea of actually reversing this mindset and giving people the pro package, so to speak, and then selling the little idea, the thing that's the smaller package, and reversing that mindset and focusing more on influence and building culture rather than trying to focus on actually just making money up front.
Yeah, sounds like I was a lot smarter last year. Yeah, but I believe that. I believe in giving away your best stuff. And, if people want to support, they can. But I think we live, especially in a modern day, where people don't have to pay for software if they don't want to. They can pirate anything they want. So you have to make people want to support you. You have to encourage them to feel good about it, so they want to buy and support your products. Because otherwise there's no need for them to do that. So that's the best copyright protection there is to, have people love you or appreciate you at least.
Let me follow up on that because, when we transitioned to using computers in our music years ago, I mean, that was one of the biggest things. And we understand with new technology, there's a cost associated with that it really restricted music creation to the pro users. But one thing I think I've seen from the music community is there's been so much creativity, so much musical innovation because of accessibility, and price drives that. When I have access to the sounds and the tools that I need to be creative, I can do that. What should limit me from making music as a third grader, compared to, someone who's been in the business for 20 years? There shouldn't be any barriers there. Because, if I had a $15 Casio keyboard, the creativity would still be there. But now that we can enhance the sound and the capabilities of the music community, I think it's a rising tide. We lift the whole music community when you're able to provide great sounding tools at an affordable price to the masses.
Yeah.
Or, yeah, I don't know exactly how it is in the VST desktop community, but in the iOS community, we all support each other. And, I'm happy to jump on Twitter and promote everyone's apps when they came out. We don't see each other as competition. We're all in this together, this emerging technology of mobile music.
Yeah, and you brought up a great segue that I wanted to ask about, which is that you focus primarily on music on iOS apps, and what do you think that that does in terms of the workflow for musicians and end users? Why the decision to go away from desktops where you could traditionally sell a product for more money to go to a to essentially an ecosystem where a lot of companies and a lot of developers are giving away their products for free?
Yeah, it's really crazy because, iOS started off as kind of a novelty and then like a niche. And now like people like KG and Henny, they're getting Grammy nominations for producing things all on their iPhone and iPad. And it's really inspiring to see. So I'll let KG talk more about that.
Well, I think it's just a natural progression as technology gets better. Um, you think about it, our phones are more powerful than the computers we ran 10 years ago to create the same stuff. One thing for musicians, and Fabian, you talked about this a lot, latency is a big issue for us, being able to capture that idea accurately, to be able to monitor what you're doing. That's a big part of the creative process. So, as technologies just evolve, why not delve into it when I have access to it at any given time, any given moment? As I said many times, inspiration doesn't always hit us when we are in the studio. When I'm at the beach or I'm at a park, that's when I feel inspired. When I'm with my family or a tune just comes in my head, having the ability just to pick up a device, I don't have to worry about a long boot up sequence and then to log into this DAW. I can just have it at my fingertips individually. But as we continue to, really progress in the development of software tools or apps, I can create that whole idea in this single space wherever I am. And it doesn't require a lot of desktop real estate connected to, uh, audio interfaces and other devices and other peripherals that I need. I can really create at any moment, which is an incredible change in the way we make music.
Amazing. And that brings me to another question just about the creation process. So is it all mobile, including the mixing, and or is it that you maybe hash out a rough idea and then go to the desktop, or is it completely mobile?
So, it can go a couple different ways. I think from a conceptual standpoint, like from initial thought, going to an iOS device is the perfect place to start. And for Henny, it's something that he really integrated with me. I'm the type who will sit down at the piano or electric piano and start with an idea. It starts with the melody with me. Now that I have access to it on my device, that's a good starting place. And apps have developed and workflows have started to form that we can take it from initial idea all the way to this is a really good demo or mix for me to then take it to the next step. As we continue to see more apps develop, more tools develop, I think we are on the cusp of being able to do everything in that iOS device. I'm not going to say we're all the way there yet because we're tinkering around and still trying to find workflows that work for us to get there. The easiest way to get from idea to final production. So usually, a lot of our mixing, like finalization, mixing, and all that stuff, it happens outside, but a lot of it begins on the iOS device. And as we create apps like House Mark One, I don't have to go and drive to my studio to get the sound of that, electric piano. I've got it right here in my hands. But I say this to all developers: the hardware is there. I mean, it's there. It's about now creating the tools to help people get to that final product.
Mm.
And I think we're on the cusp of it.
And what do you think is where what is that cusp for you where you say, oh, I really want to, I've been doing this on my iPad or on my iPhone, and now I'm ready to take it I need to take this to the desktop? Is it the mix down, mastering side of things, or is there a certain point where do you feel that iOS doesn't quite get you there?
Yeah, it gets to the mix down. I mean, for us, we've used quite a bit of DAWs from a desktop perspective, and have explored, quite a bit on the mobile side. It really is trying to find what is that great in between. Apple's done a lot with GarageBand, their baby brother to Logic, and it seems like it's now going a lot from GarageBand back to Logic of some of the features. But finding what is the great medium in between of, and I look at it from iPad perspective because it's about the input, the way I am able to input ideas into that device, as a great idea starter. But then when I need to start recording audio, and then take that audio to mix, I don't, there are a couple products or a couple apps out there that are able to do that, but I don't know if they're the all in one. One of the biggest things is, and this is the beauty of the stuff that AudioKit's been doing, is having this AUV3 capability. For us as producers, we want to use multiple things and then integrate it into something where we can have a MIDI clock or some type of start stop function that everything can play in sync. It's a big thing with music since the creation of MIDI, to have all these devices talking to one another, all these modules talking to one another. If we can get to the point where we're integrating that into a fully packaged, not only MIDI app, but it's just as good on the audio and audio editing side. That's where it's we basically stop. I've seen it happen on the video side. There are great apps out there that you're able to do a lot of editing in, but once we've got the idea, then it comes down to arranging and editing, and we're just not, I think, 100% there yet. But that's when we switch off from maybe the mobile side to going into a studio or to a DAW to then create.
Amazing. And what do you have any future plans or future collaborations that you could talk about at this point? What's next for AudioKit and for KG and Westview?
Matt, what's next?
I need a vacation. When it comes to collaborations, I mean, some of you are probably watching, well, hey, this is great, Matt. I'm glad you live right next door to two Grammy winners, but like, what do I do? How do I make an app like this? And I would say, like, reach out to like musicians that might be just like below that top tier, that might have like a lot of free time right now during the pandemic. Like, I mean, if you email Elton John, he's probably not going to email you back, but think about like maybe someone big in your region that's kind of a big figure that you could collaborate with and make an app with. And I think just starting from that and getting that to the musician before you write a line of code is just like a really profound and fun experience. Because we do this because it's fun, right? Audio programming is really, really hard, as all of you can attest. And like, we could make more money probably writing accounting software or something like that. But I just think the beauty of life is being able to work with other people and create something magical. So I would encourage everyone, when you're starting your next project, to maybe reach out to a musician right now, because like, we all need to lift each other up, and we're all in this together.
Absolutely.
Yeah, and I think, Matt, that's a great point. At the end of the day, we've got to make this community better. I think from musicians to music technology, and we've got to collaborate and figure out a way to get there, because it's going to keep moving. I mean, we've seen what technology has done to the music industry in the last 20 years. I mean, it's basically changed the way we consume music. It's changed the way we get paid for music. And technology is not slowing down. It's going to keep moving forward. It's going to keep driving us. So hopefully we can create better products that it strengthens our music community and the way we are making music.
So it sounds like there are two sides to the equation of really making a successful music app, which is the of course the technological side, and then you have the user experience side, the side of people that are actually going to be using the product, and actually the dialogue of those two sides becoming coming into something that actually has a combination of both of the benefits of both of those sides. And we see it with like larger companies, of course, the Abletons, the Native Instruments. They have, of course, people that they're dialoguing with and that they're speaking with, continually getting feedback from. So it's not really just, sounds like it's not just about sitting in your room, closing your windows, locking your doors, and just putting your head down and making some code. Yeah. I guess I could drop the mic right there. So, do we have any questions, Teamer? Oh, you're muted. Classic.
Sorry, classic. Forgot to unmute myself.
Yeah.
So we have a question from the chat on YouTube from Aura Audio asking, there are many traditional effects such as dynamic compression, EQ, bit crusher, etc. But how do you implement these effects in a way that creates a unique product?
Great question.
Like, how do you make something new and unique with like traditional effects?
Yeah.
Well,
Yeah, so-
Matt, you want to go ahead?
Okay, so first of all, is that Evan from Georgia Tech? I think it's Aura Audio. So hi Evan.
Yeah, that's Evan.
Good guy. So let's talk about too. This goes into like promoting your app as well. It's like, so let's say you have a new synthesizer, and it's made up of all these different DSP components. You might have like an app description that says, my new synthesizer has 3 LFOs and 2 oscillators and 5 kinds of filters. I mean, but that's kind of like boring, and like that doesn't inspire. It's almost like maybe how I might describe my significant other? I wouldn't say like, oh, she's 5'8", blonde hair, red nails. I would say like, oh, she's there for me when I need her, and she helps lift me up, and she always has a kind word to say, et cetera, et cetera. So I guess just getting that mindset of like the benefits of what you're trying to achieve. It's not just like, oh, this is an effect. This is, you can go to like, oh, how is this going to inspire a workflow or a music making process to help create?
Mm-hmm.
Can I jump in on that?
Of course.
Please.
So let me give you an answer from the music perspective. There hasn't been a lot of innovation in instruments. If you think about traditional instruments, the electric guitar, the piano, violin, strings, these instruments have been around for years, and we've always seemed to find a new way to get creative with them. I think allowing space for creators to create, and that goes back to the point from earlier. Yeah, I'm going to give you an electric piano that might have a phaser on it, or it's not going to be anything that's just so crazy new. But if you give me an opportunity to get creative with it and to use it maybe in a non-traditional way, I think innovation comes from there. But without access to it, you've already lost the battle. So I think your question is from these traditional products or effects, how can you make them more creative, even combining them? But you have to have access to do that.
Yeah, it really makes me think of early drum machines and how hip hop producers use the drum machine was originally meant to be a replacement for drummers in the studio, but hip hop producers took it and it created a whole different sound that obviously doesn't sound like a real drummer, but at the same time has broke into new dimensions in terms of creativity in the way that they were able to take that tool and use it in a non-conventional way.
Yeah, no, 100%. I mean, and just one other that's a great example. It's not only about making that product, like let's say the drum machine, but then when you combine the drum machine with a real drummer, you get a whole different other thing. This analog meets electronic merge it's I think probably one of the most creative things that's happened in music in the last 40 or 50 years. 1982 to 1985 were some incredible albums because they had both of those worlds meeting each other.
Yeah, and I have an interesting question, just in terms of breaking into those new dimensions. Of course, many of the instruments that we see on iOS and on desktop are imitations of things that we see in physical hardware, or very close imitations, that are based on many of the same concepts. But then you see other things that are starting to break out into new areas in terms of the way that users are able to interact with music systems. I mean, do you think that things will continue to stay in the same relative region in terms of 88 keys or a keyboard where you actually play a sound, or do you think that as we move forward that more things are going to happen and that these workflows are actually going to be more creative as we move forward?
It's a hard question. And, we've seen that with instruments like, Roger Lynn and his instrument, and, Jordan Rudess and his GeoShred instrument, just kind of new interfaces and way of working and taking advantage of this workflow. But at the end of the day, it's kind of hard too, because musicians kind of want to see, a virtual representation of what they're used to. So I think as developers, we need to kind of push things forward. And I guess to Evan's question earlier, he's like, what if we have all these effects? What can we do with them? Maybe you can make some sort of like cool drum processor, and it uses all those effects in a certain way for a certain niche genre of music. And you have like certain weird controls where you push and pull things to make your cool drum sounds.
Yeah.
And I think going hyper niche by combining, existing effects and going niche with it, with like presets, maybe with like, great producers in that genre, makes for a really nice little product.
Amazing. Any other questions, Teamer? Oh, you're muted again.
Not at the moment, no. I think that's it from the chat for now.
Yeah, that's great. And if people want to try out AudioKit and interact with that community, Matt, how do they do that? How do they get in touch with you?
AudioKitPro.com, and we have links to our GitHub. It's very active. We have a Slack group. All are welcome, all skill levels.
Yeah. And how is it different from Juice, AudioKit? Like, how would you say that it's like Juice in a lot of ways, or that are there some distinct differences?
Well, it uses Swift, which is a high-level language. So if you don't know C++ or C++ scares you, that might be a good place to start with AudioKit. Or if you're Apple-centric, it does use native Apple tools. But I'm a big fan of Juice, and we may even do some Juice plugins down the road. So nothing's out of the question.
Yeah, that would be awesome. And Juice has been great over the past 2 years about starting to come out with higher level extractions that make it easier for people that don't know a lot about development, like myself, to actually get in and actually make some actual DSP processes and useful tools. So that's great.
Yeah.
Great. I think this is a good place for us to wrap up. Anything else before we start signing off?
I just want to thank you both for your insights. I definitely learned a lot as well, and that's really interesting. Yeah.
Yeah.
Cool stuff.
Thank you. This was a blast. This is a real honor to be on this podcast.
Yeah, an honor to have you.
Thank you.
Yeah, thank you very much. Great. So I guess we could sign off. Yeah.
So I just realized I've never actually used any of your apps. So which one should I try first?
We have a free and open source one. Our most popular one is Synth1, and that's probably a good place to start. And all the code is online. If you want to get some pull requests in there, we'd love to have you.
Great, that sounds great. I'll check it out later today, maybe. Thank you.
I love it. Love it. Great. So I guess a couple announcements before we sign off. As Teamer had mentioned, ADC is 1 week away. If you haven't registered for ADC, be sure to go to audio.dev, and you can actually find out more information about the schedule and what we have coming up. And also, we will be live streaming one of the tracks from the Juice YouTube page as well. So people who have not purchased a ticket will also be able to interact with the conference. Anything else that we'd like to mention, Teamer?
Yeah, so the main track will be streamed, as you mentioned, but also a lot of people ask, like, what happens to the other tracks? And so the other tracks, you get access to them directly if you obviously register for the conference and you're at attendee. But if you're not, then they will be published after the conference. So you will eventually get access to this content, which will be free for everyone on YouTube eventually after the conference.
Yeah.
So I'm just mentioning that because a lot of people were asking this. And yes, eventually all the content will be free and available on YouTube. And the other thing I'd like to point out is that this, it's not just watching stuff on YouTube. We also have a socializing platform based on Remo where you can actually interact with people. There's this really cool, there's these like virtual tables and virtual seats, and you're like thrown into video calls with people, and you can network with them, and it's like really cool. So encourage you to check that out.
Yeah, definitely. And yeah, go ahead, Timur.
And I guess the other thing that we have is obviously this meetup. So please submit your proposals. As Josh, you already mentioned this.
Yeah, we've already got the December guests locked down, and we're really excited to tell you, even though Timur doesn't even know who those guests are, but we have an exciting meetup coming up, and with some really special guests. And thank you once again to these special guests that have joined us today, Matt, Kennard, and Fabian. And
yeah, it's really exciting that we can keep this going, and like, thank you so much for joining and having another great meetup this month. It really means a lot. So thank you so much.
Yeah, thank you.
Thank you.
And we will sign off.
All right. Well then, have a great evening, everyone.
Have a great evening. Thank you very much for tuning in.
Thank you. Bye.